Hello all, welcome back to my channel. Please like, subscribe and press the bell icon so that you don't miss out on any of the upcoming sessions. In today's video, I'll be explaining you the Kmp algorithm. Kmp algorithm is a string pattern matching algorithm that finds if a given pattern exists in another string or not, and if yes, then at what index. Firstly, why do we even need any special algorithm for pattern matching? To answer this, let's first understand the naive approach. In naive approach, what do? We match each and every character of the string and pattern, and wherever there's a mismatch, we reset the pointer. So let me explain you how we do this. So whenever we want to do, we will match this the A of the string with the pattern. Okay, we are starting with I equals to 0, J equals to 0. Both have matched. Okay, we increment the pointers by 1. Now string of I and string of J again matched. So we increment the pointer again by 1. So now your I is 2 and J is also 2. So a string of 2 and pattern of 2 both have matched. So now I becomes 3 and J also becomes 3. Now at this position, we figure out that the string and pattern are not matching. So what we are going to do? We are again going to start the pattern from J equals to 0. So we are going to reset the pattern's index or the pointer to J equals to 0. And how about the pointer or the index for the string S? That also we will be resetting. And to what value? To I equals to 1. Because we have started from I equals to 0 in the beginning. So now we will be starting it at I equals to 1. And then again we will be doing the comparisons. Now again we will see, okay, A have matched. A and B, they don't match. So again we will be resetting the pointers. Now I would be 2 and again J is 0. So likewise you will match and in the end you will be finding a match because the pattern exists towards the end of the string. So if we are going with this approach, what would be the complexity? It would be big O of m into n, where m is the size of this, where n is the size of this string and m is the size of the pattern. Now your m and n can vary to like 10 to the power of 4 as well. So in that case, the complexity or the running time would be very high. Then to resolve this problem, Kmp algorithm comes into picture. Kmp algorithm produces or gives the output result in linear time. The complexity for Kmp algorithm is big O of m plus n. Now, if you have observed one thing that while we were doing the pattern matching, some of the characters of string S were already compared with the pattern P, but we are again and again matching them. For example, in the first iteration, when we were doing A. So A, these characters were already matched. We found a mismatch at the characters C and A. But when we found a mismatch and we reset the pointer, we again started from this A. So A and B, these two characters, we are matching again and again. Similarly, when we come to this part, A, I would request everyone to please do a dry run for even for the naive approach for these string and the pattern. It will help you understand little further. So similarly for this, we will be finding a mismatch at this position. Sorry, not at this position, but at D point. And then again, we will start from the beginning. So that's the problem with the naive approach. We are doing the comparison over and over again. With Kmp algorithm, we will be doing these comparisons only just once. So let's understand how the Kmp algorithm helps us achieve pattern matching in a linear time. So in Kmp algorithm, there is a pre-processing step. In pre-processing, what do we do is we create a pi table, or we also call it as the LPS table. Now I'll tell you what does this mean. So LPS table means a longest prefix that is also a suffix. Prefix that is also a suffix. So what is meant by here is that I hope everybody knows what do we mean by prefix and suffix. So prefix always starts with the leftmost character of the string, and suffix always starts with the rightmost character of the string. So for this pattern, this was our pattern. For this pattern, let's see what are the prefixes and suffixes. So the prefixes are A, starting with the leftmost, then it is AA, then AAB, then it is AABA, and then it is AABAA. But in this Kmp algorithm, we are interested in a proper prefix. When I say proper prefix, a proper prefix means a prefix that is not the actual string. So this becomes your actual string, so we will discard it. We are just interested in the ones that are the proper prefixes and suffixes which are not the original string. Now let's see what are the suffixes here. One is A, AA, BAA, ABAA, and then it is AABAA. But again, as we discussed in the case of prefixes, we are not interested in the suffixes which are the original string. So there are 4 prefixes and 4 proper suffixes. Now when we are creating the LPS table, we have to figure out all those proper prefixes that are also a suffix. Is A a prefix as well as suffix? Yes, it is. So A is 1. Then AA, is it in the suffix? Yes, it is. AAB, no. AABA, no. So there are 2 strings that are suffixes as well as the prefixes. Now I'll explain. Let's in another terms, it is any part of the string that is again repeated in the later half. So if you see, this AA is being repeated in the later half of the string. So this will help us skip the characters while doing the pattern matching. So in pattern matching, when I am saying that Kmp algorithm helps us achieve in the linear time, in that case, whenever there is a mismatch, we need to know that these many characters we have to skip, and we don't have to start from the beginning of the string. We will be continuing from the point where there is a mismatch. So in that case, this LPS table or the pi table will help us. Now let's see how to create this pi table. I am not explaining the algorithm right now. I am just explaining you how you can create this LPS table. So it is A, B, A. This is the same pattern that we were talking about. For the sake of simplicity, what I am going to do is I am going to mark them as 1, 2, 3, 4, 5 rather than using the index as 0. I'll be using the index as 0 for all other references, but just for now, for explaining on how to create this LPS table, I'm using the indexes as 1, 2, 3, 4, 5, okay? So this is 1, 2, 3, 4 and 5, okay. So A, this is the first occurrence in the string, so we will mark it as 0. Then again we are seeing an A, okay. Has this come earlier? Yes, it has come. At what index? At index number 1. Then we are at B. Has B occurred earlier? No. So it is 0. Has A occurred earlier? Yes. It has occurred at index number 1. Okay. Has A occurred earlier? Yes. It has occurred at index number 2. Now, if you observe, I have marked it here as 2 and not 1. Why? Because this AA pattern is the entire pattern that is matching here. AA. So, this A has occurred at index number 1, whereas this A has occurred at index number 2. Okay. So now this is what we have as the pi table, or you can call it as the LPS table. Okay. This is your pi table. Now we will use this pi table as a reference to understand the algorithm. Now coming back to our original string, let me do one thing. I'll just copy paste this string again so that you don't lose the track of this page. So okay, so this is our string, this is our original string, and the pattern that we want to find is AABAA. It is occurring in the end. Now, before we do a pattern matching, we have created this pi table. Now, what we are going to do is, we are going to initialize j equals to 0 and I equals to 0, both as 0. And now what I will be doing is, I will be marking the indexes as 0, 1, 2, 3 only. Okay. I'll explain the algorithm or the actual code on how to generate this LPS table a little later. But for that, and right now to understand the algorithm, I have mentioned the indexes to be starting from 1, 2, 3, 4, 5. Okay. But let's come back to the original computer world, how it starts. So now we see, okay, so now we are going to start one by one. We will be matching these patterns. Okay. I equals to 0, j equals to 0. Does the string of I and the pattern of j, does it match? Yes, it does. If it does, what we are going to do is, we are going to increment I and j both. Okay, your I is 1 and your j is 1 now. Again, they have matched. So, I becomes 2 and j also becomes 2. Again, they have matched. I becomes 3, j becomes 3. Now, here is a mismatch of the characters. So, pattern of 3 and string of 3 are not matching. Okay, so what we are going to do is, we are going to reset j. J equals to what? Okay, so j equals to LPS of j minus 1, that is j equals to LPS of 2 and that is your 0. Okay, so again we are going to start from j equals to 0 and I is still 3. So pattern of 0 and string of 3, are these matching? No, they are not yet matching. And right now our j is also 0. So whenever j is 0 and there is a mismatch, we are going to increment the I pointer. So now we are going to do I plus plus, which means that I will become 4 and j is still 0. Okay, so now I is pointing to this. It means that all the characters, whenever we are doing an I plus plus and there is a mismatch, it means that whatever the string has gone in the S so far will not match. We have to do a fresh start. But notice that we have not iterated these characters over and over again. We are just iterating over them once. Okay, so now let's see. So j equals to 0 and I is 4. So this is your 4. Okay, A and A match. Perfect. I is 5, j is 1. Again A and A matched. Okay, I is 6, j is 2. B and B matched. Perfect. I is 3 and I is 7 and j is 3. Again A and A matched. Perfect. So I is 8 and j is 4. Okay, A and D. Now here is a mismatch. Okay, so A and D is mismatch. Now what we are going to do is, j is not yet 0. Also, we will also check whether j has reached the size of the pattern. No, it hasn't. If it has reached the size of the pattern, it means that we have already found the string. So I am not going to those boundary conditions. I'll explain them with the algorithm. Right now I'm explaining them the code, I mean. Right now I'm just explaining you how it works. Now j is 4 and I is 8 and here is a mismatch. So how we are going to update j is with the help of this condition. J equals to LPS of j minus 1. So j is 4, LPS of j minus 1 is 3, so that is 1. So j equals to LPS of 3, that is equals to 1. So now our new j is what? 1. Okay, that is here. Again we will do a match. Does pattern of j and s of I match? No, they don't match. Again we are going to do is j equals to LPS of j minus 1, that is LPS of 0 and that is equals to 0. Okay. So we are again going to do j equals to 0. We are again going to match. Does this pattern of j and s of I matches? No, they don't match. And at this point our j is also 0. So what we are going to do is, we are going to increment I. So I has become now 9. Okay. Now I is 9 and j is 0. Again start a match. A and A. Does this match? This A and this A. Yes, matches. Increment both. Again this A and this A. Yes, it matches. Increment. B and B matches? Yes, it does. So again, we have incremented them. Again, A and A matches, perfect. And the last character has also matched. And after this, we see that all the characters in the string S have exhausted and all the characters in the pattern P has also exhausted. And J is also equals to M, where M is the size of the pattern. It means that we have encountered a pattern that is present in the string. And at what point does it start? It starts at this point, that is I minus j. The index at which it exists is I minus j. Okay? So this is how the Kmp algorithm works. Now, how does the code looks like to it? I'll take up in the upcoming section. So please stay tuned to understand the code for the pre-processing, that is for this pi table or the LPS table, how the code looks like for this and how the actual code looks for this Kmp algorithm. Please stay tuned. I'll be uploading it in the upcoming sessions. Thank you for listening.